Section 10.3, Example 1, Bulls and Cows. Our first game will be based on an old code-breaking game called Bulls and Cows. It might remind you of the game Wordle, but don't worry if you haven't played Wordle before. We'll be able to play this game against the computer. Randomness plays a critical role in this game, as we'll see. Section 10.3.1, How the game works. In this game, Player 1 thinks up a secret code, which is a sequence of 4 digits. Player 2 has to figure out what that secret code is. In our version of the game, the computer will be Player 1, and the human player will be Player 2. Here's how it works. The computer will randomly choose 4 distinct digits, duplicate digits aren't allowed, as the secret code. For example, it might choose the digits 1862. Then, you'll guess what you think the computer's 4 digits are. For example, you might guess 3821. For each guess, you're told 2 things. First, you're told how many digits in your guess match the corresponding position in the secret code exactly. We'll refer to digits that are in the correct place in the secret code as correct. Say that the secret code is 1862, and you guess 3821. The second digit in both your guess and the secret code is 8, so that's a match. There are no other matches, so you would be told for this guess that the number of correct digits is 1. Second, you're told how many digits in your guess exist at some other position in the secret code. We'll refer to digits that are in the secret code but in a different location as misplaced. Let's again use 1862 for the secret code and 3821 for your guess. The third digit in your guess is 2. It doesn't match the third digit of the secret code. That's a 6. But there is a 2 somewhere else in the secret code. Similarly, the fourth digit in your guess is a 1. It doesn't match the fourth digit of the secret code, but there is a 1 somewhere else in the secret code. All told, 2 of your digits, 1 and 2, exist in the secret code, although they don't match their expected position. You would be told from this guess that the number of misplaced digits is 2. You can use these clues to narrow down what the secret code could be. Wordle. If you've played Wordle before, you might notice some similarities between Wordle and our game here. Wordle uses letters, and ours uses digits, but the type of feedback you receive for your guesses is similar. In both cases, you're told about letters or digits that are in the right or wrong place. In Wordle, you're given a clue about each of your letters on its own. For example, if the first letter of your guess is H, you might be told that the H is in the word but in the wrong place. By contrast, in our game, you're not given hints about each digit individually, but instead are given hints about your guess in aggregate. Still, we hope you're struck by these similarities, and by the fact that you're building something that resembles a recent, worldwide phenomenon of a game. We found a free version of Bulls and Cows that you can play at this link. We recommend that you play a few rounds of the game before continuing, just so the way the game works is crystal clear in your head. Note that they use the terminology bulls instead of correct and cows instead of misplaced. In Table 10.1, we've provided an example interaction with the game. We've included a comments column to convey our thinking and what we learned from each guess.
Table 10.1, Example of playing the game.
The challenge of the game is that you have a limited number of guesses in which you must successfully guess the computer's secret code. In our example from Table 10.1, we took 7 guesses to guess the code 2675. For each guess, we were given the number of digits misplaced and the number of digits correct to guide our thinking. In the free version of the game that we just mentioned, you're not allowed to include the same digit multiple times in your guess. For example, the guess 1231 wouldn't be allowed because of the 2 1s. We'll maintain this restriction in our version of the game as well. Section 10.3.2, Top-Down Design. Our overall task is to write a program to play the Bulls and Cows game against the computer. Let's do top-down design on this large task, just as we did in chapters 7 and 9. What has to happen during this game? Answering that question will help us break down the game into smaller tasks. To help us with this, we took the rules of the game in our example, and thought through what happens at each step of the game. Each of those high-level steps appears in Figure 10.2, so let's break them down one by one.
Figure 10.2, Steps in the Bulls and Cows game.
We'll start with the setup. For us to be able to play the game, the computer has to randomly generate a secret code. We need to ensure that the secret code doesn't have any duplicate digits. To us, this sounds like something that's sufficiently complicated and self-contained, so it should be its own subtask function. After the computer generates its secret code, we can move to the gameplay itself. Here's where the player starts making their guesses. We might think that we could just use input to ask the player for their guesses, and thereby avoid having a separate function for this. But we do need to ensure that the player enters the correct number of digits, and that they don't include duplicate digits in their guess. This is more than we can do with a single call of input, so we'll make this its own function as well. Once the player makes their valid guess, we need to figure out two things: how many digits are correct, and how many digits are misplaced. Should we have one function to carry out both of these tasks? Or maybe we should have two functions, one for the correct information and one for the misplaced information? We see good arguments on each side. If we put the tasks together into the same function, we keep the player feedback centralized in one place, and that may make it easier for us to confirm it's written correctly. On the other hand, having two separate functions would make it easier to test each type of feedback, correct or misplaced, at the expense of spreading out the logic for the feedback across two functions. We somewhat arbitrarily chose to use a single function here, but if you were hoping to have two separate functions, we encourage you to try that on your own after you finish working through this section. Let's take stock. We have a function to generate the computer's secret code. We have a function to get the player's next guess. We have a function to get the correct and misplaced clues for the player's guess. Those are three major subtasks that we're happy to split out of our top-level function. Is there any other subtask to split out? There's certainly a little more work to do in our top-level function. For example, we need to detect if the player's guess matches the secret code, and end the game in that case. We feel that we don't need a separate function for that, though. To determine whether the user's guess equals the secret code, we can use Python's double equals operator, which tells us directly whether two values are equal. And to end the game, we can use a return statement to end the top-level game function, and thereby stop the program. Similarly, if the player uses all of their guesses without getting the secret code, then we need to tell them that they lost the game. But again, we should be able to do this with a small amount of Python code. As such, we'll stop here with our main top-level function calling three subtask functions. When we worked through our spelling suggestions problem in Chapter 7, we needed to break one of our subtasks into sub-subtasks. But here, each of our three subtasks will be manageable as a single function. For example, let's think again about our first subtask, generating the computer's secret code with no duplicate digits allowed. Could we split any sub-subtasks out of here? Maybe we could have a function to check whether there are any duplicate digits in a proposed secret code. Then, we could keep generating secret codes, calling our sub-subtask function, until it tells us that there are no duplicates. That would work. But we could also just generate the secret code digit by digit, and not allow a duplicate to be added to the code in the first place. This latter plan seems to not need any sub-subtask to be split. Now let's think about our second subtask, getting the player's next guess. We could split out a sub-subtask to tell us whether a guess is valid. That is, it has the correct length and has no duplicates. While we could surely do that, it's not much of a stretch to do this with a couple of checks in the subtask function itself. Did your mind just go back to our example in Chapter 7 about valid passwords and detecting valid passwords, where we split the check for validity into its own function? If so, the difference is that checking whether a password is valid is likely a more substantial task than the validity checks we need here. It would certainly be okay to break this into another subtask, but we'll move forward without doing so. We've already argued that our third subtask is fine as is, so we'll stop our top-down design here. We'll name our top-level function play. In it, we'll call three functions corresponding to the three subtasks that we just identified. We'll call the function for our first subtask, generating the computer's secret code, random string, the function for our second subtask, getting the player's next guess, getGuess, and the function for our third subtask, providing feedback to the player, guessResult. See Figure 10.3 for this top-down design depicted as a tree.
Figure 10.3. Top-down design for the bulls and cows game. The topmost, leftmost, function is play, which calls random string, getGuess, and guessResult.
Section 10.3.3. Parameters and return types. Normally, we define the types of parameters and return value for each function during the top-down design itself, but we wanted to discuss that separately here because there are some subtle aspects this time. For example, you may already be imagining that we'll use integers to represent the secret code and guesses, but, as we'll see shortly, this isn't the best choice. We'll make some decisions about how we'll represent the data for all the functions before we write each one. The play function is our top-level function and the starting point for our game. It would be possible to have this function take no parameters, Somewhere in the code of the function, we'd have to hardcode the fact that the secret code has 4 digits and that the player gets, say, 10 guesses. But that wouldn't be very flexible. What if we wanted to play a version of the game where the secret code is 7 digits and the player gets 100 guesses? We'd have to go into the code and make all the necessary changes. So, to make the game easily configurable, we can provide some parameters to this function. For example, rather than always having the secret code be 4 digits, we could use a parameter to allow the length of the secret code to be set to whatever we want. Similarly, rather than putting the maximum number of player guesses directly into the function, we could make that a parameter as well, so that we can easily change it. Then, all we need to do to alter the gameplay is to call this function with different values for these parameters, without having to mess around with the code of the function itself. Using parameters and variables to avoid magic numbers. The number of allowed guesses and the number of digits in the secret code are good examples that we can use to explain an important principle in code design. This principle is that when we write code, if a number can be a parameter or variable, it should be. This principle ensures the code is as versatile as possible. When programmers see a number being used, rather than a friendly name, they call this a magic number, and that's what we want to avoid. In our discussion about the number of guesses the player gets or the number of digits for the secret code, those should be parameters if we abide by this principle. At some point, these parameters need to be given concrete numbers for the code to work, but we should assign them values at the highest level of the code as possible. For example, the player might set these parameters when the game starts. To help adhere to this general principle, whenever you see a raw number, for example 4, in the code, ask yourself if that could be a parameter or variable. More often than not, it should be. Adding these parameters is another example, as per our discussion in Chapter 3, of making functions general purpose rather than unnecessarily restrictive. Our random string function is the function that generates the computer's secret code. Why did we put string in this function name? Shouldn't we be returning a random integer, like 1862? What does a string have to do with this? Well, the problem with returning an integer is that the secret code might start with 0. A secret code like 0825 is a perfectly valid 4-digit secret code. But 0825 as an integer is 825, which doesn't have enough digits. The string 0825 is just 4 characters that happen to each be digits, so there's no problem with starting a string like this with a 0. Beyond that, let's think ahead about what we'll eventually need to be doing with the computer's secret code. We'll need to compare it digit by digit with the player's guess to determine which digits match. Using indexing on strings will give us easy access to each character of the string, which is exactly what we need. It's more challenging to access each individual digit of an integer. Integers don't support indexing. So our random string function will take the required number of digits of the secret code as a parameter and will return a random string of that length, where each character in the string is a digit character. When we talk about digits in a string, all we're referring to are the characters of the string. They happen to be digit characters, but they're still characters, just like A or asterisk. Don't be confused by the fact that the string might look like a number. Here's an example showing that these strings work the same way every other string works.
See this code?
What about getGuess, the function to get the next guess from the player? As with random string, this function will need to know the number of digits of a valid guess, so we'll make that a parameter. It will return a string giving the player's guess. Finally, let's talk about guessResult, the function that tells us how many digits are correct and how many are misplaced. This function will need both the player's guess string and the computer's secret code string in order to make comparisons between them. So we'll need this function to take those two parameters. We need to return 2 pieces of information, the number of digits that are correct and the number of digits that are misplaced. So we'll return a list of 2 integers. Section 10.3.4, Implementing our functions. Having completed our top-down design, we can now work with Copilot to write the code for each of our functions. As always, we're going to write the functions in order from bottom to top. This means that we'll first implement our 3 subtask functions, and then ultimately implement our top-level play function. Random string. As always, when working with Copilot to generate code, we provide the def line and docstring, and then Copilot writes the code. In each code listing, we'll also provide some guidance about how the code works. We want our random string function to take the number of digits in a secret code as a parameter and return a random secret code without duplicates. In the code for this function, We might expect Copilot to use random.randint in a loop that continues running as long as we don't have enough digits. To avoid adding duplicate digits, the code would add a random digit to the secret code only if that digit isn't already in there. We found such a solution in our Copilot results, and that's the one we've chosen to present in the following listing.
Listing 10.1. Function random string for generating a secret code.
We're not focusing on testing in this chapter, but even if we were, we wouldn't include exact tests in our docstring for this function. That's because this function has a random result. Randomness can make testing functions difficult because it's hard to control the random values you get. What we could do is add a test to our docstring that at least checks that the generated secret code contains the correct number of characters, that there are no duplicate characters, and that each character is a valid digit. You can also test such functions by running them, and observing that their result is always within the bounds of your random range, and that the results appear random. If you did carry through with testing, you'd find that we have a perfectly fine implementation of this function and that there's no need to do more. If you just want the game to work, you can skip to where we start writing the getGuess function. If you'd like to learn more about Python and function design, we'd like to take this opportunity to spend a bit more time looking at different solutions to this function. We encourage you to check out the Copilot suggestions in the window that appears when you press Ctrl-Enter to see some of the other possibilities. For example, we can start with a list of all the integers from 0 to 9, and then use a function called random.shuffle to shuffle that list into random order. Then, all we do is take the first length integers from that shuffled list, where length is the length of the secret code. And that's the secret code. We're guaranteed not to get any duplicate digits because the original list that we shuffle doesn't have any duplicate digits. That version of the function might look like the following listing.
Listing 10.2. Alternative solution for the function random string.
If you want to learn more about what this code is doing, you have the tools to do that. Don't assume that the code is out of your grasp. You can ask Copilot to explain the code. You might get an explanation like the following. Human. What does my random string function do? GitHub Copilot. The code is a Python function called random string that takes an integer length as input and returns a string of the given length, where each character is a digit from 0 to 9, and with no repeated digits. The function first creates a list of digits from 0 to 9 using the range function and the list constructor. It then shuffles the list using the shuffle function from the random module. This ensures that the digits are in a random order. Finally, the function uses a list comprehension to convert the first length digits of the shuffled list to strings and join them together into a single string using the join method. Overall, the random string function generates a random string of digits with no repeated digits, which can be useful for generating unique identifiers or passwords. What's a list comprehension? You don't need to figure this out on your own. You can ask Copilot to explain it. Human. How does that list comprehension work? GitHub Copilot. The list comprehension in the random string function is used to convert the first length digits of the shuffled list to strings and join them together into a single string using the join method. Here's a breakdown of how the list comprehension works. 1. str of d for d in digits of colon length is the expression that generates the list of strings. It takes each digit in the first length elements of the digits list, converts it to a string using the str function, and returns the resulting string. 2. Digits of colon length is the iterable that the list comprehension operates on. It takes the first length elements of the digits list, which have been shuffled randomly. 3. The entire list comprehension is enclosed in square brackets, which creates a new list from the elements generated by the expression. Finally, the join method is called on the resulting list of strings to join them together into a single string with no separator between them. Some of this text from Copilot may not be completely understandable, but you could keep asking it to explain what you're unsure about until you're satisfied you understand how this is working. We didn't need to show this second working solution for this function, but we want to take this opportunity to remind you of how far you've come. As you've progressed through the book, you've been developing tools and techniques to understand and create software, as well as the confidence to learn and keep learning more. Getting back to the problem at hand, let's code our next function. Get_guess. Our getGuess function takes the number of required digits as a parameter and returns a valid guess from the player. Remember that for a guess to be valid, it must contain the right number of digits, and it must not have any duplicate digits. Here's what we got from Copilot in the following listing.
Listing 10.3. Function getGuess for user input.
That while loop condition is a complex one. The final part, len of set of guess exclamation mark equals length, is responsible for checking whether the user entered any duplicate digits. It's using a Python set to do that. We did see this trick back in Chapter 7, Section 7.7.7, but that was a while ago. So, if you need a refresher, don't hesitate to ask Copilot for an explanation of that line. Guess result. Our guess result function takes two strings as parameters, the player's most recent guess and the secret code. It returns a list of two integers, the number of correct digits and the number of misplaced digits. This is a tricky function to get right. So even though we haven't been showing the tests we'd want to run in prior functions, we're going to provide some explicit tests in the docstring for this function. We're adding these docstring tests because the logic for this function is going to be complex enough that it will be hard to determine whether the code is correct by solely reading the code. For our docstring tests, we'll need some good example cases of different secret codes and user guesses to ensure the number of correct and misplaced digits returned by the function are as expected. Of course, per Chapter 6, you'd likely want to add even more test cases if you were interested in doing serious testing. Our first test case is,
See this code?
the correct return value here is 1, 2, because there's one digit that's correct, the 8, and two misplaced digits, the 2 and the 1. Our second test case is,
See this code?
the correct return value this time is 0, 4, because there are 0 correct digits, but all 4 digits of the guess are misplaced. Here's our complete docstring, including test cases and the code from Copilot.
Listing 10.4. Function guess result to get the result of a guess.
The use of elif is subtle here. If it were written as if rather than elif, then the code would be wrong. Do you see why? If not, try conversing with Copilot before continuing to read our explanation here. Suppose that the if condition guess of I double equals secret code of I is true. In that case, we increase correct by 1, and we skip the elif statements. Remember, the elif statements run only if the preceding if and any preceding elif conditions are false. Now imagine we change the elif to an if. If the if condition guess of I double equals secret code of I is true, we'd still increase correct by 1. But then, we'd check the guess of I in secret code condition, and this one would be true as well. After all, we just said that guess of I double equals secret code of I, which proves that guess of I is indeed somewhere in secret code. So, we'd erroneously do the misplaced plus equals 1, which we certainly don't want to do. It's a matched digit, not a misplaced one too. Play. We're done with our subtask functions. Now all we need to do is write the play top-level function. Our play function takes two integers as parameters, the number of digits in the secret code and guesses, and the number of guesses that the player has to guess the secret code. It doesn't return anything, it just plays the game. Our final prompt and code for this function is given in the following listing.
Listing 10.5. Function play for playing the game.
If we ran our program now, nothing would happen. That's because we haven't called the play function yet. We always need to remember to call our top-level function. To call it, we can add this line below the play function.
See this code?
The 4 means that we're playing with 4-digit codes and guesses, and the 10 means that we have 10 guesses to correctly guess the secret code. You can change these arguments to tune the game how you like. Let's give our game a whirl before we continue. We'll show our first few guesses and then our final guess.
See this code?
We've succeeded in designing a computer game, which is a very different kind of program than the other programs we've written in this book. Our computer game interacts with the user, has randomness, involves 2 players, the human player guessing and the computer player providing the correct and misplaced clues, and has winning and losing conditions. That's a lot of new stuff. However, we also hope that you see how much we've learned and brought forward from prior chapters. We're still doing top-down design, still designing functions, still testing code, still reading code, and still conversing with Copilot. You hadn't written a game prior to this chapter, but essentially you already had the skills to do that. Don't let a seemingly new type of program or app stop you from trying to do it. Section 10.3.5. Adding a graphical interface for bulls and cows. You might be disappointed that our game doesn't look much like a game you've recently played because there are no graphics, just text. For example, there's no nice area to type in, no buttons to click, and no graphical interface at all. We've already argued why we focus on text games in this chapter, but it doesn't mean that turning this game into a graphical interface version is entirely out of your grasp, because you could interact with Copilot to see if it can help you get started. The challenge is that programmers create graphical user interfaces using a style of programming called event-driven programming, which we haven't taught you yet, and is too large to teach in this chapter. You can likely read through event-driven programming code and make some sense of it, and that's what you'd need to do if you ask Copilot to write code to produce a graphical interface. That said, if Copilot doesn't give you what you want, it may be difficult to fix without first becoming familiar with event-driven programming. There's a nice book on game programming that includes graphical user interfaces and event-driven programming in Python called Invent Your Own Computer Games with Python if you'd like to learn more. Event-driven programming. Event-driven programming is commonly used for programs that interact with users. At a high level, the program sets up a way for the user to interact with the program, for example by pressing buttons or entering text, and then just sits and waits for the user to do something, sometimes updating the state of the game while waiting for the user input. Once the human interacts with the game, the code recognizes this interaction as an event, and each event has code associated with it that should execute when the event occurs. For example, when a user clicks the Quit Game button, it triggers the code that needs to be executed when the user wants to quit, for example, saving the state of the game and exiting the program. We were quite impressed by what Copilot gave us when we asked it to create the graphical interface for Bulls and Cows, so we'd like to show you how well it did. The code is somewhat readable even without knowing event-driven programming. For example, you can probably find the title of the game and change it. To do this, we asked Copilot Chat the following question. Human, can you convert this program to use a graphical interface instead of a text interface? Copilot responded to us by laying out step by step the changes that we'd need to make to do so. It then rewrote the code so that the game now used a graphical interface with buttons and edit boxes rather than a text interface. See Figure 10.4 for the new interface. The code to generate this interface is on the website for the book, in case you're interested in running it yourself or learning about the code.
Figure 10.4. The graphical interface for the game as provided by Copilot. Note that it shows the secret code, presumably to help with testing. You'd want to remove that before playing the game.